Good afternoon, everyone. My name is James Powell. This is my Twitter right up here. I'm coming across really loud, so I hope maybe we can turn that down a little bit. I am a Python programmer. You can tell from my accent that I'm not from anywhere local. I'm actually from Australia, but I come here via New York City, where I run NYC Python. So these are all the meetup groups in the world that are Python related. And I run this guy right here. Number 5 on the list of all the meetups and the largest Python meetup group in the world. It is one of the most active meetup groups in New York City. So here's my dopey photo right over here. We have 2 headline events every month, office hours every Tuesdays, and on Saturday and Sundays we have workshops. It is a really awesome community, and I really hope that conferences like PyData will help bring that level of enthusiasm to London, the level of enthusiasm that we see in New York. I also help organize the PyData conference series. So what you're going to see here is I just tweeted that, and then what I'm going to do is I'm going to sign out of Twitter, and then we'll sign back in as PyData Conf, and then retweet myself. So look at that. That's one of the great things of running a conference series. You can retweet yourself the moment you tweet. Oh, wow, I'm so popular. So there you go. I also am in New York City running a conference that may be of interest to some of you guys. I work in quantitative finance, and on the 14th of March, Pi Day, I'm running a conference in New York City dedicated to the use of Python in analytical finance. We have a lot of really cool speakers. Dr. Hilpish, who gave the UX presentation earlier today, will be speaking. I also have Kirat Singh. He's the guy who introduced Python to both JP Morgan and Bank of America, which I think the two of them alone constitute some of the largest uses of Python in production. We're talking 12 million lines of code bases, thousands of programmers, just an enormous amount of attention. We also have someone from Quantopian. We have somebody talking about bootstrapping, discount curves. Professor Jared Lander from Columbia speaking about statistical problems in finance, and a lot of really cool talks. So if you're in New York in March, this is something that you definitely want to go to. And if you know anyone in New York, you should tell them about this. So this presentation, this workshop, is actually a combination of 2 different CPython workshops that I've given. The first one was an overview of CPython for a broad understanding, and the second one was what the title of this workshop was, which is embedding. And each of these are about 45 minutes long, so I think we can fit them into the time. The first workshop is just a motivation of the use of CPython to better understand what's going on underneath the hood and to develop some of these skills of being able to debug and really understand how Python works and what Python is. I think that, in my own experience, you can get up to speed with Python really easily if you can understand how things are implemented in CPython. It gives you a way to conceptualize how things work and what they do in a way that is very difficult to gain by just reading documentation or just kind of playing around. One example of a question that I was able to answer for myself very easily using these techniques is, we know that we have dictionary unpacking in Python. So let's make this bigger. So we know we can do something like, we can do something like this. And we could do something like that, right? We can unpack this dictionary into keyword arguments. But we can also do that. But one could never be an argument, right? So how can we keyword unpack something that isn't itself ever possible to be an argument? Similarly, this can contain none. So why does this work? Because you'd think if naively the interpreter went in and said, well, A equals B, 1 equals 2, none equals none. This is nonsensical. And with a few seconds in the CPython interpreter, you can see exactly why this is. And maybe if we have time towards the end, I'll show you. It's actually a very simple case. Similarly, you can see why. Actually, I don't want to give away one of the treats. So we'll get to that when we get to it. So that's kind of the thrust of this, just kind of playing around, learning how to build Python, how to debug it, looking under the hood, and answering a couple questions. This workshop is orientated around answering 3 specific questions. Namely, these are real questions that I've had to answer for people. So for example, you have all these custom objects in your system. So in your 12 million lines of code, you have all these custom objects flying around. And you don't know what happens when I call a method. You can use the inspect module, and the inspect module will say, well, the source code for this method belongs over here or belongs over there. But there are more fundamental questions than that you might want to answer. For example, how does the dispatch for the mul and rmul add and radd work? If you have two objects and they implement all these pieces of the data model and you try and multiply them times each other, which of those multiplication functions ever gets called and why? And that's the first question that you can answer for yourself very easily. The second question is, this is a fun one, and people. So the second question is, you have this hash function, which gives you the hash of objects. So if the hash of 1 is 1, the hash of 2 is 2, the hash of -2 is -2, but the hash of -1 is -2, and why is that? And what does it mean for it to be this case? Because you can see that for every other natural number up to a certain size, the hashes correspond directly to their values, except for -1. So some of these weird corner cases, when you look and you see the answer for that, it's blindingly obvious. And it is actually a very interesting answer that has some real implications on where and when you can use the hash function. And the last point here is something that I have yet to get around to doing, but we submitted a PEP. The first time I gave this workshop, we submitted a PEP, or a bug fix, which later became a PEP project, to undo some of the restrictions around the syntax that's allowed in a decorator. So in a decorator, you have the @ symbol, and then you have something that follows that. And what follows that isn't just an expression. It's what's called a dotted name. So there's certain structures that aren't allowed there. And I showed there's only 3 changes to 3 lines of code that you have to make to allow any arbitrary expression there, such that you can then do something like this. And that would be legal syntax. So that's the third question that we'll be able to answer in the first, I don't know, about 45 minutes of our talk today. So the notes for all of these are in a gist on GitHub. Let me take that and blow that up for you guys so you can download it. And while you do that, there we go. And we'll stick it on the bottom of the screen. And while you do that, I'll go through the very first steps. So there you go. Those are the notes for everything here. I'll give you a few seconds. We can take our time. It's a very nice, slow, leisurely pace. I'll actually also give you an overview of the next few steps of this presentation. So after we look at answering some of these questions, some of the preparatory work of using GDB, compiling Python for ourselves, we're going to look at the very high-level embedding. And the very high-level embedding is a way to embed a Python interpreter at a very, very high level into some arbitrary C or C++ application. On the topic of embeddings, there are a million different embeddings in the world. There's Boost Python, there's Swig, there's all sorts of different binding and linking and embedding mechanisms. But we'll look at the 2 direct major ones that don't require any external dependencies, and then we'll look at 2 somewhat novel ones that I came up with when putting together this presentation. So we'll look at the very high-level embedding. We'll look at the pure embedding. Then we'll look at how Cython is actually an automated formulation of the pure embedding, and what you could do if you took the ideas behind Cython and to their extreme to get what I call a zero interpreter embedding, which then bears some very interesting meaning on what Python is as a system or as a structure. How do you really conceptualize what the code that you've written is in a very philosophical and existential fashion? And then the last one we'll look at is what I call Py2SO3, which is embedding Python interpreters within each other. Now, on that topic, and while you're still trying to grab this, I'll say that on the plane I tried 2 other mechanisms for embedding Python interpreters within themselves, one using CFFI and the other was using C-types. And it ended up that these ended up being very, very similar, and I was speaking to somebody from Continuum earlier as well to see if there's any way to do that. And it turns out that actually embedding a Python interpreter itself is more perverse and more difficult than it sounds. But it's a lot of fun. So let's start with the basics, with the very beginning. So we'll go to python.org, the nicely updated, refreshed, beautiful python.org, and let's see if I submitted some bug requests because a lot of stuff on this page is still out of date, so let's see if they fixed that. All their past events, they pulled out the community section, I think. Let's see, because the past events were still displaying 2000, there we go, these are up to date. Oh, look, there's my conference right down there. And we'll go to downloads, and we will download the source code for Python 3.3.4. And if you go down here, you'll see you can get it as a compressed source tarball. So this is like a cooking show, so I'll show you that, and then I'll show you over here where I've actually already done all the work. So in the first step, let's blow that up, I'll just wget that, and then I'll extract it. And with it extracted, we can take a look at what's inside. And what's inside this directory, there's a little bit of a tour guide that we have to endure to really figure out where to go to look for different things. So in the notes, I talk about a couple of these directories. Some of them aren't terribly relevant to what we want to do. So PC isn't terribly relevant for what we want to do. There's also PC build. And these contain things, for example, if you want to compile Python using Visual Studio, none of which is immediately relevant to using GDB in order to debug Python, in order to learn how the language works. And there's also a Mac there's Mac stuff for all sorts of different, I guess, idle on a Mac and different other Mac-specific pieces. So first is doc. So doc contains all the restructured text for all the documentation that you see on the Python website. And if you're stuck on a plane and you can't figure out how something works, and help doesn't give you anything interesting, and you want to figure out where's the documentation for this, things that may not be in doc strings, like the data model or different embeddings, you have to grep through this and read through this. And that's what I did on the plane, because I forgot to download everything. So I went to doc, extending, embedding, and you can see this is all the documentation text from the website. And that's the very high-level embedding right there. More interestingly, if you look at include, you can see all of these are all the include files. So when you need to link against Python, say you're writing an extension module, or you're writing some crazy embedding, these are all of the .h files that you should already see on your system. They should be in user, lib, x. On my system, it's here, Python. No, it should be user include. There we go. And then it's in here somewhere. Python, maybe? Yeah. Python 2.7. And you can see these are all the things which, if you need to build an extension module or some module, and there are more extension modules out there than you might think. So Postgres or I think MongoDB has an extension module as well. And whenever you need to link against any of these exported symbols, all the header files are in this include directory. The next very interesting one is lib and modules. So lib contains all the source code of the standard library where the module itself is written in Python. So you'll see a lot of modules in here that themselves are in pure Python. For example, let me find a good one. Because some of these are actually kind of tricky, because they're actually not entirely written in Python. Argparse, for example. Argparse and some of the cute ones like anti-gravity are all here written in pure Python. So when you need to find the source code for it, it's right here. Now what you'll see is in modules, you have all the extension modules that are part of the standard library. So the math module itself, when you import math, the actual module is an extension module. Oh. Get file, maybe. So it's a built-in module. You can't find the source code. It's not written in Python. And the source code is actually here in math.c. So, and what you can see also is that for many modules, like itertools, there may be actually so itertools is another perfect example. All of this stuff is written in C. And then for other modules like regular expressions or JSON, there's a pure Python component and a pure C component. And sometimes if they both coexist, you may see an underscore before the name of the C component. And then outside of that, there are only two more directories that are of immediate interest. Objects, which contains all the source code for all of the internal pieces of Python. So all of your function objects, dictionary objects, list objects, and all the methods corresponding to that are here. So you can see list object at the top there. And this contains all the source code for processing lists. And if we go to the very end, we'll even see all the methods that you have. So PyList, object, so list reversed. And if we find this, there we go. You can see those are all the methods that are defined on a list: copy, clear, append, extend, and so forth, and so on. And the other interesting directory is Python. And this contains all the source code for the actual running Python interpreter. Of interest here is one specific file This also contains two tricky things. The sys module and the sys module and the built-in module are both in here because they're actually one special case of a module that's not, it's written in C, but is so close to the running of the interpreter itself that it can't just be loaded as an extension module like everything else. But a very interesting file in here is ceval.c. And ceval.c is kind of the start and end of this entire talk. ceval.c is basically the interpreter itself. If you scroll down in here, you'll see a function called pyeval eval frame x. And what this guy is, and if you scroll down, you'll see a bunch of all these register. So we know that this function needs to run really quickly because they're making sure that everything gets register allocated. And then this is Python 3, so there'll be a long talk about computed gotos in here, which is not relevant to Python 2.7. But if we keep scrolling down past all these definitions, we'll see a very interesting line of code. It's setting up some state, and then there we go. We have an infinite loop. What this is a loop. And if we scroll into this guy, we'll see inside this loop is a bunch of case statements. In Python 2, they're actually case statements. The target will desugar into a case statement. We have an infinite loop, and inside that loop, we get the next opcode, and then we switch. If we go up, we'll see a switch opcode. So what we have is an infinite loop that processes every bytecode, and a switch statement that says, OK, what's the current bytecode? Process this line of code. What's the next bytecode? This line of code, and so forth and so on. So that's a whirlwind tour of the CPython source. What we're going to do is we're going to build it and install it and start debugging. So this is how I usually build it. I like to build it all in one step. There's only one special thing here. By the way, these are all in the notes. So anyone who's built source code who's built binaries on Linux before knows there's a configure, make, install cycle. I add a couple of small things to that. I build with J9 to make this faster. And I build in a prefix directory, so I don't want to clobber anything on my system. This is why I like make and CMake. This is a little bit trickier to do. But I want to put it in source Python 3.3.4-build, just so I know where things are. And then, very importantly, I build with debugging symbols. And I've added some C flags that are passed to GCC to add even more debugging symbols. Most notably, I can now debug macros. And this is extremely useful because there's a lot of macros all over the place. And sometimes it's hard to determine what is this symbol. Is it a macro? Is it a function? And I can actually see what the macro text expands to, which allows me to debug things really, really, really easily. So if I were to do this, then it would build. And this has already been built. So I'm going to show you one way to get a foothold into debugging CPython, and a very, very easy way, even if you've never really done this before. And you don't have to do anything but have access to the source code and know how to use grep. One thing I will say, though, is if you want the source code, if you go to hg.python.org, you can get all the source code if you don't want to download onto your own computer. You just want to read it with all the comments and all of the version control, all the commit comments and whatnot. You can see all the source code is here, hg.python.org. So there are two modules that are extremely useful for debugging Python code. Please, in the back. Yes, you can use LLVM. One limitation of using LLVM is that some of the toolchain is not as, it's a better tool, but it's not as mature. So certain things like exporting macro dwarf information isn't yet implemented. Or tab completion doesn't work as nicely. Small bits and pieces there. The scripting is much nicer, but small bits and pieces make GDB not the ideal tool, but a very comfortable and very useful tool to use. I don't know if they have reverse debugging, but GDB has reverse debugging, just small pieces around the edges. So I've done this with LLDB. I'm not as familiar with LLDB, but I also know that it hasn't been around as long, so some of the edges haven't been polished, and some additional features haven't been added yet. OK, so the two modules that are very useful, even if you don't ever want to touch, you don't ever want to read, write, compile, you don't want to write or compile, but you're OK with reading C code, are the dis module and the inspect module. And I pulled one. So one thing you can notice from this is that, oh, I hate this stupid debug build. This is 3.3.4, which means we're going to do something wild. Give me 1 second. Nope. We're going to rebuild this just to remove. You see how it says refs? This is one indication of a debug build. They made this an option in 3.4, I believe they made this an option. In 3.3, it'll print after every line. It bugs me. So one thing that I do just to maintain my own sanity is I run a custom interpreter that does not. So we'll watch this hack the matrix at the bottom of the screen here. But I'm just building CPython, and I'll just install it, and that way I'll get rid of these extremely annoying refs. Because for the purposes of what we're doing here, we don't need to count ref counts. We're not looking for memory leaks. It's very useful if you're looking for memory leaks, but in this case, we just want to play around with what's happening internally.
A really quick question. Is it specific for Python 3 or also?
So the refs. So the first part of this presentation is in Python 3, and the second part's in Python 2. All of this material should be generally applicable to both of them. Python 3 has a little bit nicer layout of its source code. It's a little bit easier to read, and a lot of crufty old code has been removed. For example, in Python 2, when you're looking into in Python 2, when you're looking into some functions, you'll see a lot of old code that references old-style classes and a lot of code that references new-style classes, and that all that branching is no longer relevant in Python 3. So you have a much cleaner code base, and you don't get distracted by things like, is this a... And the terminology is a little bit tricky. So when you look at the Python 2 code base, sometimes you'll see referring to things as instances or classes, and it may not be clear immediately that, oh, they mean old-style classes versus new-style classes. That distinction is gone. So let's make install. And make install prints out a bunch of stuff, so we'll just pipe that to dev null. See, in the course of 2 minutes, we have already produced our own custom Python interpreter, which will solve a real problem for us, which is getting rid of this annoying ref count at the end of every line. And let's see, am I on fast? Yeah. OK, there we're done. OK, so there we go. So from this, import this. And from inspect, import get source and get source file. So say we have some function that we have somewhere in scope. So let me think of something that's also written in Python. So I have to think of a module that's written in Python by itself. Argparse, import argparse, I think. No, from preprint, import preprint. Right? So say somewhere you see a symbol, preprint. You have no idea where did that come from. Get source file does a fairly good attempt of telling you where the source code for that is. So this is the first thing that I do. Some function isn't operating the way that I want. I'll see where's the source code for it, and I'll start reading the source code. So if pprint is doing something that I can't understand, I'll go to pprint.py. Very recently, I was trying to help somebody debug why they couldn't properly overload JSON encoding. And the very first thing I did was I saw, OK, where does JSON the dumps come from? Or where does the JSON encoder dumps come from? And I looked at the source code, and everything was clear. So that's get source file. Get source is also very useful. It'll actually give you the source code. If it can determine the source code, it'll give it to you. And since this is Python 3, we have to do that. So that's actually the Python source code that it found. Of course, this doesn't work on source code in C because none of that information is maintained. And then the other very useful tool is the dist module. So when we want to figure out even lower level than something that's happening at the Python level, what's happening at the bytecode and below level, the dist tool is extremely useful. And what it does is it takes some object, a lambda, a function, a class, and it disassembles it and gives us the bytecode disassembly. So maybe we want to figure out what happens when we swap two variables. So we'll create a sample function that all it does is swap the two variables. And we want to figure out what actually happens behind the scenes. Then we disassemble it, and the disassembly tells us exactly what we want. And I'll interpret this for you. The very first column corresponds to the actual line of Python code. So the first line would be the signature. The second line is xy equals yx. So that's what this 2 means. 0 to 16, those are the actual offsets of the bytecode. So each bytecode's about 3 or 4 bytes long. So the 0 is your load fast. Then a couple bytes later, you have another load fast and a rot2 and so forth and so on. You can see that one of these is a little bit small on the other. So rot2 is only 1 bytecode long because it doesn't take any arguments. And then the other ones are about 3 long. Then you can see in the penultimate, in the second to last column, that's actually the argument that's passed to it. So you can see that for each one of these that has an argument, these are 3 bytecodes long, or 3 bytes long for each bytecode. And then in parentheses is an interpretation of the argument. So actually, if you were to look at the bytecode itself, you'd see you'd see load fast, which is some number, some opcode number, and then you'd see a 1. And what would happen is that 1 would be interpreted as the variable y. It would be an offset in an array that corresponds to all the local variables. But that doesn't really help us too much. We want to figure out what does rot2 do, or what does binary multiply do. And the next step that we have is we can just grep the CPython. This is how I started learning about CPython. I looked at bytecode, I found things which looked a little bit curious, and I grepped the source code for them. So there. And we can see that rot2 appears in a bunch of different places. And we can kind of guess from the names what these are. So compile is probably the compiler that takes the code that you write as a string and compiles it to an AST. Peephole, we can maybe guess that it's maybe a peephole optimizer. So that's not really relevant. But ceval.c, and this is literally how I learned what ceval.c was. I saw rot2 is in ceval.c, and in Python 2, instead of being obscured by this macro, you actually will see case rot2. So you'll say, wait a moment, well, why would there be a case statement? Oh, because there's a switch statement inside a for loop that's actually dispatching all these opcodes to the code that actually runs. So we can see on line 1389 in ceval.c, we have the code for rot2. So there we go. So this is what happens when you swap a variable. It loads x and y onto the stack. It swaps them. So it gets the top element, the second element, and then it just sets them in the other direction. And then it just stores them back. And so that's really all there is to it. It's a very simple example, but you can see that this approach of grepping for bytecodes can tell you what is actually going on behind the scenes. And when you get to something that's more interesting, like call function, you can see what really happens when you call a function. Or in one of the next examples, we're going to look at binary multiply. And you can see where that goes. And this is the first step to figuring out what's happening. Especially things like build class or build function, you can immediately go in and you can start reading the source code and see what is actually happening behind the scenes. For the example earlier that I showed where you keyword unpack, that was very easy to find out. So when you keyword unpack, you have, and I don't even have to run this code. I just need to disassemble it to see what the bytecode is. It's call function KW. So that means you call a function with keyword arguments. Right there. And you can see all 3 of these fall into this block of code here. And if you look through this, there's a lot of obscuring information. But right down here, you get to this function xDoCall. And that's what's actually being put right back onto the stack. So this is what does the call. And an xDoCall, now there's one thing I need to do, which is I need to set up ctags. We go down and we can see if this has a keyword, if this function takes keyword arguments, and what you gave it was not a dictionary, it'll pull all the elements out in its own dictionary. But at the very end of this, you get where the meat is, which is all it does is it takes that argument that you've passed it and it passes it to another function called PyObjectCall, which uses it directly. Which means there's no step here which checks that all the elements in the dictionary that you passed it were actually valid keywords. So with star unpacking, with double star keyword unpacking, you can actually pass a function keywords which it couldn't even possibly ever have because they get passed through directly to PyObjectCall without ever being checked for validity. The question here is how could you use this for evil? And that's a question for you guys to think about over the next 30 or 40 minutes. Is there something you could do here to make use of this? I don't think so, though. So this is how you can get started in understanding CPython. You don't have to compile it. You don't have to use GDB. You don't have to do anything special. Just look at bytecodes and grep for them and just try and start reading through the code. But I'll show you in GDB what you can do once you know this information. So in ceval.c, I found rot2 on line 1389. So what I'm going to do is I'm going to load Python in GDB. I'm going to start it. And I'm going to create my function. And this function doesn't do anything particularly interesting. It only replaces them in a local scope, but it at least makes use of this rot2 keyword. But it doesn't actually do anything particularly useful. But you can see that it works. And what I want to do, if I want to really figure out what goes on behind the scenes, is I can Control-C to get into GDB, and I can put a breakpoint on the line that I identified. And then I can continue running this. And then when I call my function, I've now broken in the C code where I'm processing this instruction F1020, or the bytecodes corresponding to it. Now, there's not too much that we can see interesting about rot2, because it just loads some stuff, then rotates them, and then stores them. But there is some other very interesting things that we can answer for ourselves from this point, which is if we do backtrace, we can see a trace of all the functions that we had to hit before we got to this stage. And it gives us an idea of the structure of the Python interpreter. So if we've been programming C for any length of time, we know that all C programs start in a main function. So Python starts in its main function, which is stored in python.c. So when you type Python at the command line, it immediately enters this function main in python.c. And this calls a pymain. And in this particular case, we call then run file, then pyrun any string flags, then pyinteractive loop flags, and this is what gives us our interactive interpreter. Then we get into running a module, and then finally at the top you can see those are the C functions that correspond to running actual Python code. There is pyeval, codex, and then framex. And then finally, since we should be a couple deep, we're actually calling a function. So we called a function to get into this, to do the swapping. So you can see here's the barrier, this call function. So down here is everything up to the interactive console. This is the actual calling of our function f, and then above that are all the stack frames corresponding to what happened inside f. Now there's one thing that we can do very interesting at this point, which is we can source tools gdb libpython.py. And now when we do the backtrace, it gives us rich Python information about everything at every level, including the state of the built-ins and the state of the globals. So this actually makes it a fairly reasonable. It's not, if you wanted to debug a very large Python application where all the interesting things were happening in Python, use PDB. It's going to be way easier for you. But if your problem is some interaction with a C library or a C++ library or something bound, this actually becomes a very usable approach because you can see everything that's happening internally. And for example, in my local scope of pyeval framex, you can see I have f, which corresponds to the frame. And it even tells me in f with those arguments. So I can see a lot of information of what's happening at the Python level with this set of GDB macros. Or actually, these are no longer GDB macros. These are, GDB has the ability to use Python for scripting, and these are extensions to GDB written in Python itself. So that answers a couple of extra questions for us. Because one thing that I always like to do when I am faced with a new project, with a new C or C++ application, is figure out, how do I get into this application? What's the actual chain from starting the application to the functions that I'm supposed to be looking at or extending or working on or implementing? Where does the main function and where does that main function go? And this tells us your Python interpreter starts here and ends up right there. I find that very useful for having a very holistic understanding of the program. So that takes us to this point in our lecture. So the first question we're going to look at is, and I'll show you two more things. There's a couple of small interesting things given by the macros we have. So we saw this target that I told you desugars to a case statement. So we can do info macro target. Well, I'll show you first list. List gives us all the source code surrounding where we have our breakpoint. So we can see the rotate to source code right there. And we see this target. And I told you that this desugars to a case statement. And you can see it desugars to actually a couple more things. It says opcode equals op, and then it has arg, and so forth and so on. But at the end, you can see case op. So you can actually figure out what these macros end up doing. You don't have to go searching for where that macro is. You can immediately see the source code that will run. Additionally, you can do things like you can step. Now, I can't go into any functions here. So there's a step and a next. One goes into a function, one steps over the function. There's not one steps into the function and one goes to the next instruction. In this particular case, everything happens at that very top level. It happens inside the interpreter for loop, so there's no functions for me to really step into. There's a couple of macros here, and you can see what these macros do. And you can see pretty straightforward stuff, exactly what you'd expect. So there's a stack in the C code, and set top, second and top are just pulling elements out of that. And I could show you reversing, but that's very tricky. So that's one really neat feature that GDB has. You can run code backwards. You can allow code to, you can set a point where your code starts. You can allow it to run, and then you can run it backwards to see what happened to break that. And it's very, very useful, but it does bring up one point, which is this is such a low level of debugging compared to using PDB and debugging at the Python level, that if you were to try that, it would take you years and years to execute even very simple functions. The reverse adds a huge overhead because it has to store all of the register information, and all the state. And there's so much that happens in CPython to get you from the invocation of one function to the end, and so many different calls that happen that you end up not having enough time for that. That's also another problem in the second part of the tutorial, where if we look at breakpoints, you have to do some stuff with conditional breakpoints, just because there are a lot of C calls that correspond to a single Python call. So we're going to start looking at the next few questions. So the first question is, which mol? So we have two classes, and they both implement a mol. And they're very simple. There's nothing terribly interesting in them. They subclass from int, and they just print out. They don't even return any value. They just print out which one was called. And so if we stick this into our interpreter, so that should be, now I'll do this guy. If we stick that into there, those are our definitions, and then we'll call a couple of these. So we have two custom objects with mol implemented, and if we create two of them. And we can actually switch the order of these two screens. And if we multiply foo times bar, foo's mol is called. If we swap the order, bar's mol is called. If we multiply foo times 10, 10's mol is called. And if we multiply bar times 10, that mol is called. So we can see a pattern emerging. Whichever object is first that has an underscore mol implemented is the mol that gets called. Now, if we are a little bit richer and we add in an r mol, we see, again, fairly predictable behavior. So again, if we do that, and we do foo times bar, we see foo's mol is called, bar's mol is called, the r mol is called. So the next modification we can say is, if we were to have an r mol, then the dispatch is whichever is the most custom object that has a mol called, that comes first, is the one that gets called. And if it has an r mol implemented but it comes last, then that's the one that gets called. But where it gets a little bit tricky is here, when they have both mol and r mol implemented. And when we notice that there's one difference here. Bar is now subclassed off of foo. So they're no longer subclassed off of a common int. This is now a subclass of this guy. And that adds one more dimension to this. And if we do this, we'll see. So that wasn't expected. This is totally different than our first example. You can see now bar's r mol is called. And you can see that bar is now dominating the calls between foo and bar. And the question is, why is this happening, right? There's some set of rules somewhere that's defined that are in the documentation. But we need to figure out, and we need to know why this is happening. Because we may have these objects floating around our system. And you may want to have some thorough, consistent way to conceptualize how they behave. So we're going to use a very standard technique to do this. I'm going to create a function that multiplies two things. I'm going to disassemble that function. Oop. I'm going to disassemble it, and we can see a bytecode. And that bytecode is binary multiply. If I grep the source code for binary multiply, so and I'll find it only in a couple of places. And one of those places is ceval.c on line 1473. So if I look at ceval.c on line 1473, there we go. Now what I'm going to do next is I'm going to open up another tab, and we're going to run this and set a breakpoint there and trace it. So there we go. We're going to set a break. We're going to run the interpreter first, because there's a lot of setup code that happens there, and we don't want to break on any of that setup code. So we'll get into a functioning interpreter. We'll define our function. Then what we'll do is we'll set a breakpoint on line, on line 1476. 1476, and we'll continue, and we'll call our function. There we go, and we broke right at the line that we wanted. Now what we're going to do is we're going to step into this, and we're going to step down until we actually learn the answer to our question. So we'll step into this. So now we're in objects abstract.c, and if we look at the listing of the code, we'll see there's something interesting here. So in here, I'm going to open objects abstract.c on line 890 or so. And you can see here's where it determines if one of these is a sequence. So you can do something like the letter A multiplied times 10, or repeat A 10 times. Or you can do a list with a single element to multiply. So that's where it does this. But in our case, none of this is a sequence. So what we'll end up with, we can see just very generally, is we'll go into binary op1. And so in binary op1, we'll just step into that. So now we're in, we're in binary op1 right here, and abstract.c as well. So we'll go back into our source code. If we had a larger screen, we might be able to look into this very easily. And we can see it's doing some determination if this guy can actually be interpreted as a number. And if so, we end up calling, where are you? So slot 1, so we see if they're both numbers, or they both have these this substruct of elements for the numbers, the mul and the rmul. And if so, then we end up calling here. This is actually where the magic happens. This says, so this is a little bit tricky to put into words, but essentially the structure in the C level that corresponds to this object has some substructures. And those substructures implement some of the common protocols that we use. One of them is sequences and iterability, one of them is mapping, and the other one is numbers. So if you look at the data model, you'll see a bunch of functions in there that can be classified in some ways. Some of them don't have any specific classification, so init, new are common to all objects. But only numerical objects will have add or multiply or div defined. Similarly, only sequences will have things like iter or next or length defined. Similarly, only mappings will have getItem and setItem defined. All objects, of course, will have getAddr and setAddr defined. And so what it's doing is it's trying to determine if the slot exists, if on this object it has this substruct of methods corresponding to it being a user-defined number. And if so, it's going to pull it out. And then here, it's going to do some determination to see is W and V are the arguments that we passed. Is W a subtype of V? And if so, we use W's R method, or we use W's R method with these two arguments. Otherwise, we use V's method with these two arguments. Now, this is all generic for all binary operations, but in this case, it says if W is a subtype of V, use W as multiply and multiply with these two. Otherwise, use V as a multiply and multiply these two. Otherwise, there's a slow path as well. But this is the main point. So the behavior that we saw before is whichever comes first in the sequence, unless one's a subtype of the other. And if that's the case, then you use the most derived subtypes multiplication methods instead of the least derived subtypes. And if we look in the documentation, it says that exactly. If the right operand type is a subclass of the left operand's type, blah, 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 that's the answer to our question. And we can figure this out ourselves just by stepping through a couple of C functions and seeing literally how it's implemented. So I'll show you the backtrace, and you can see where we went. We started call function and fast function are the invocation of F. Then we went to pi eval frame X. That's where we put our breakpoint. It took us to pi number multiply, abstract.c. And that took us into binary op1. And that's where the answer to our question lie. The next question that we'll answer is this hash, -1 versus -2. And so just to reiterate the question, we have, so we'll stop GDB, and we'll start it back up again. We have this behavior where hash of 100 is that, hash of 99 is that. If I do, you can see I could even do this, right? So up to 100, all the hashes correspond to exactly those numbers. And the only one weird case is hash of -1 corresponds to these two. Is there a question in the back? I'm sorry? So the MRO will tell us, so the question is whether or not the MRO tells us what gets called. In this particular case, the MRO won't tell us. What the MRO will tell us is how a method gets looked up, how a method gets resolved. So on some deep nested, some set of subclasses, where this subclass is from this, subclass is from this, the MRO will tell you where you'll look for that. And it's just a linearization of where you look. So if you have some weird graph-like or diamond-like problem, it'll tell you look here first, then you look here, and then you look over here. In this particular case, you can always put a break in the CPython code and figure out what eventually gets called. In the case of the multiplication, the MRO will not actually determine which of those two. It'll only happen if you have some class that gets overridden. In this case, that's not quite what's happening in this case. In the problem that we're looking at right now, however, the question is -1, why does hash of -1 equal -2? And this is weird, because if we put a -1 in a dictionary, it's always going to have a hash collision with -2, and it's always going to go into that slow path lookup. So this is kind of weird. Why would they do this? And clearly, they must have done it on purpose. Now, there's one very interesting, and this should give you a hint what the answer is. If I start up PyPy, and I do hash of -2, that matches. But if I do hash of -1, in PyPy, it's -1. So between these two Python interpreters, this function actually returns different values for -1. In CPython, it returns -2. In PyPy, it returns -1. So that should kind of give you a hint for what the answer to this is. But in the absence of any hints, we're going to use the same technique that we looked at before, and we're going to figure out why that is, just by debugging it directly. Trust me, this is all building up to something very wild. So, same technique as before. And you can see this is a very, very simple, very pattern process. We end up calling call function. And there was a question that was given to me here by somebody who was looking at these notes, and they wanted a general procedure for figuring out where functions were. And in the amendment to the notes here, there's a very long discussion of how to debug specific functions. I will skip that, and I'll tell you that hash is in built-ins. From inspect import get module. So hash is in the built-ins module, and we know where the code for the built-ins module is. It's in this Python directory. It's one of the only two modules that are in this Python directory, built-in module.c. And in there, I can also tell you where the hash function is. Actually, no, we're going to find that. We're going to go through that process, because even though it's the same as before. It's actually kind of neat. So in this case, we don't even know where that hash function is. We know it's in the built-in module. We have no idea where that code potentially lies. Because when this gets compiled into a binary from C, outside of the debugging information, you kind of lose all the information for where the functions actually are. So you may still need to live debug to figure out where you end up. So we know that we call this bytecode call function. So what I'll do is I'll figure out in C eval.c where call function is. Call function happens to be on line 2671. So 2671. I'll continue. And I'm going to run into a problem. If I call f, I'm going to trigger the call function on the function f. In the extension of the notes, I can tell you how you can trigger some of these breakpoints conditionally to stop them exactly where you want to stop them. That may go a little bit beyond where we want to go today. So what I'll do is I'll reinstate this breakpoint, and I'll just call hash directly. Oh. So let's make sure the breakpoints. There we go. And we'll look at the listing of the source code. So we'll do next, next. We'll step into call function. And now we're somewhere else in the C code. And if we look at call function right here, we can see that for a C function, we can guess that hash is probably a C function. We'll end up with no or simple arguments, we'll end up right here. So we'll put a breakpoint on line 4053, or we'll just step to that line. So we'll step, and we can see the code as we go until we end up calling the method right there. We'll step in, and then finally, we can see Python built-in module, built-in hash. And so that tells us exactly where the source code is for what we want. Now, if we look at this, we can see the answer to our question. If the result of PyObject hash is -1, return null. And that gives us one hint. So what is this PyObject hash? And the relevance of this is as follows. The example I showed you before was not just for integers. If I were to create my own custom class like this and define hash like this, there is no way I can get that -1 to come out. It's being overridden somewhere. And we can see part of the answer in the built-in hash function. But if we go into PyObject hash, we can see something even more interesting. So what we'll do is we'll step again. So we stepped into PyObject hash. And then PyObject hash, we need to keep looking at the listing. So we'll look over here. So we'll go to built-in hash, and we'll go into PyObject hash, and we can see right, where is it? Oh, and we go into TP hash, so we have to go one level deeper, so we have to go into this guy. Sorry, I forgot there's one more level into this. So we have to step into that, and then we go into long hash, and long hash is where we want to be. So that's an objects, long object. So long hash is what gets called for the hash of a number that fits into a Python long, which is pretty much all the numbers. And long hash is down here. And then if we scroll to the bottom, there's a bunch of stuff here. Here is part of our answer. In long hash and in PyObject hash and all the hash functions, quite literally, if your hash function somehow produces a -1, it gets forcefully overridden to -2. And we can see the reason for that if we go back a couple frames, back to right here. If PyObject hash return -1, we return a null. CPython is written in C. -1 typically corresponds to an error value. So this behavior has actually infected some of the user code that you write. If your hash function to return a -1 through the call chain of where this gets called into PyObject hash, that -1 could be misinterpreted as an error code. And so as a consequence, not only do all the specific hash functions that are provided to you, like long object hash, but even the, I think abstract, no, type, even the, in here, hash. Actually, I can search for -2 in here. Even when you have a custom object, and this is all the stuff that happens for custom objects, where it calls your custom Python code, at the very end, it even says, if your custom code gave me a -1, forget about it. We're returning a -2. Because code upstream of you, code upstack of you, will not be able to disambiguate this -1 from an error code. So that's why hash of -1 will always return something. Regardless of how you force it, it'll always get a -2 out of it. And only in CPython, because PyPy, not being reliant on these kind of error codes, doesn't care about that. So that's the answer to this very weird question. And you can see that there was no real sophistication that we needed in order to get to this point. All we had to do was set breakpoints and follow those breakpoints and understand as we go. So instead of going to Lambda decorators, I want to show you some stuff about embeddings, because I think we've set a very nice stage for understanding some embeddings of Python. So we've actually done quite a bit of this preparatory work. We looked at pulling CPython code. We're going to go into Python 2 for now, because one of the last embeddings only really works. I've only done the, I shouldn't say only really works. I've only done the work to get Python 3 embedded in Python 2 and not vice versa. So this talk is limited to starting from Python 2. We've already run things under GDB. We looked at backtraces. We actually looked specifically at PyNumber multiply. In that very first backtrace, we saw these pyrun functions. And that gets us right into the very high-level embedding. So, oh, that's my IPython notebook. And that's, yeah. So, the very high-level embedding. Do I have a Python here? Yeah, I do. Bin Python. Let me go into here. And let's GDB args pwd build bin Python. So I said that if we put a breakpoint somewhere, like if we need to find a good place to put a breakpoint, so we'll just look at Python cval.c. We'll just pick some random point, maybe the PyNumber multiply, because we know we can hit that easily. So here, line 1261. We're just going to get a breakpoint somewhere. Break cval.c 61. And if we run our Python program, it'll eventually break, and we can get a backtrace going back to the initial invocation of our program. Now, where did it break? Because we haven't run any code yet. Well, all the preparatory code getting you up to the interactive console. Some of it's written in Python, and some of it will trigger some of these breakpoints. That's why I always start up my interactive interpreter, then I go into GDB to set the breakpoints. If we look at this, this tells us the history of where we went all the way back to the actual invocation of the program. And one of the functions that we'll see in here that's very interesting is PyInitialize, which starts a Python interpreter. And actually, we're in PyInitialize, so we actually need to continue. And then so we need to delete that breakpoint, because we're hitting this even earlier than that. We're hitting it in the initialization of the Python interpreter. So let's reintroduce that breakpoint and then trigger it on purpose. So we'll do, right? So here we go. So here's a nicer backtrace, and we can see this pyrun anyFileX and pyrun interactive loop and pyrun interactive one flags. If we go into python-run.c, we can look at these functions. It turns out that there's a way to get into a Python interpreter very easily. If you have some string corresponding to program code, namely something that you read from a file, you can call one of these functions to actually run it in a Python interpreter. This is a very, very high-level entry point into a Python interpreter. And a lot of these pyrun functions exist. And if you look through this file, you'll see most of these are There's a lot of extended versions of the others, and they call each other, but there's essentially one very important one, which is there's a pyrun simple file and there's a pyrun simple string. So you can either provide the interpreter with a file to read the code or with a string. And this essentially, so simple string calls string flags, and there's different versions for different purposes, but this is one way that you can get into a Python interpreter. This brings us directly to what's called a very high-level embedding. So here I have a fairly poorly written C program. This is written terribly. You can see that I take some information from actually not for standard in. Yeah, from standard in. I don't even check the bounds. I put it into an array. You know, I have a really bad bounds check here, which says if the program length is larger than the array that I've allocated, just blow up. Just very bad C code. But I have one very interesting thing in this. I'm using pyrun simple string right here to run a Python program that is pieced together from information that's provided on the command line. And the program that's being run here, it's the same program that's being run in all of the examples. So I'll show you what that looks like. It's a very simple program. Actually, it's in the notes here, which looks like this. So this is an IPython notebook that's running some Python code as well. The motivation for this talk was a talk that I saw on PyPy, which talked about the impossibility of compiling Python, which is simply not correct. And one of the examples of this that was given was, what if you have a function that takes two type names and two values, constructs things with those two types, and then executes it? So what I have is a very simple function here that takes a type, a value, a type, and a value. It constructs one value using this and this, constructs another value here, and multiplies them. And so we see some very different behavior given what we're provided. If we give it two ints, 10 and 10, we get 100 as the result. If we give it a string and 10, we get the replication of the string as a result. Similarly, let me evaluate this. If I were to give a 10 here, you can see the 10 is repeated. So there's two very different code paths that are going down in this case and this case. In fact, in the previous example, in the very first example we looked at, we saw literally these two code paths, one which repeats and one which actually does the multiplication. In all of the examples in the embedding part of this talk, we're going to be using this to motivate what we're doing. So we're going to rewrite this in a couple of different ways. You'll see in the notes that I write it in this fashion because I'm taking everything from the command line as strings. So I'll need to figure out, in order to get this int symbol, I'll need to look it up from built-ins. So I add just these two simple steps to look it up from built-ins. That way I can write everything as a string being passed in. And here in this part, you can see the same behavior as here. So this is the common example that we're using. The very high-level embedding literally just takes that code and creates it as a string. So you can see I took 4 inputs from the command line, from argv. I put one here, one here, one here, and one there. And I create a string with this. And the string just says print this guy calling this guy, this calling this guy, and so forth and so on. And then I call pyinitialize to create my Python interpreter, then pyrun simple string to just run this code. So I'll show you the code in practice. It's very simple. And if I don't give it any arguments, it'll blow up on me, gives me a segmentation fault. So this is not very well-written code, but if I do int and int, all I do is I construct a string, int 20 times int 20, and I just pass it to a Python interpreter that I created inside the C program, and it just runs it. And if I give it string 20, you can see the same thing. So this works. It doesn't do anything terribly interesting, but it does show us something interesting. This is all that the very high-level embedding is. You have some Python interpreter running inside some process space, and you just pass it strings to evaluate. Well, one difficult thing is, what if I wanted to do something with the result of that computation? Like I wanted to see what the answer was, or I wanted to multiply something by it. Pyrun simple string doesn't return anything that I can use. It doesn't return the value. What this shows is that the very high-level embedding is very suitable for when you have some C or C++ application, and you want to be able to run Python code, and that Python code may have some stateful effects, but you don't really care about interacting directly with the results of the computation that you run, because there's no way to get them back out. You've run the script from now to completion. It's almost like shelling out, but you don't actually have an extra process space. You just run it to completion, and there's no way for you to step in and to investigate what's happening, to see what the results are, to dispatch on the results. Everything just gets run there. But it could be a very nice way to, for example, in a C application without having to shell out to something else, where you might be able to still access the same memory, so you won't have to deal with copying memory from one process to another process. Run just some Python code in that same process space. But there's not too much to it. The more interesting embedding is what's called the pure embedding. So when we looked at this pi number multiply example, so we looked at it in Python 3, but we're going to look at ceval.c in Python 2. When we looked at binary multiply, we saw that binary multiply essentially corresponds to pi number multiply. Now, one very provocative talk that I've given with a really provocative talk title is Python is really close to the metal. Because everybody loves to complain about how slow Python is, and every time I'm talking to somebody, they say, well, isn't Python too slow for this or too slow for that? And in practice, it seems that people are they are very effective at getting work done with Python as a tool. So its slowness doesn't seem to be a detriment to a lot of work that's happening out there, even work that deals with humongous data sets. But more fundamentally, can you say that Python is slow in some existential fashion? My argument is that Python is close to the metal, not in the sense that you can set memory layout. So one nice thing about C or C++ is you can enforce memory layout of how things sit. And when you write a custom Python object, you have no control of what the memory layout is. You can't pack the struct or order things in a certain fashion. You can, at a very high level, ensure that things are in places that you want, but you don't have that same very insightful, you don't have that very powerful ability to structure where things are located in memory. But what you can do is you can take any line of Python code and deterministically map it to a set of lines of C code. And in the sense that Python is slow, it's not slow because it's doing some weird dispatch. It's that what that line of Python code maps to tends to be C code that internalizes a lot of very complex dispatch. So if you have a tight loop, and that tight loop is multiplying two ints, and you know those ints never get larger than 50, and you know that the multiplication of those ints never gets larger than 50, right? Python's going to be much slower at that than C. And the reason for that is C is going to see that you're only dealing with ints, and it's going to be able to translate that into assembly that can deal with ints. And it's going to keep everything in registers, and it's going to be really fast. Python has no ability to determine statically that the types of these two are constant over the expression, that the types of these two don't change, that there actually are ints as opposed to some crazy custom object where you've implemented mul or rmul. And so what happens at each step when you multiply them is you go into pi number multiply, and you have to entertain this very lengthy dispatch to figure out, well, what is this object? Is it an int? Is it a string? And you have to go down this chain. And each one of these steps costs you something. Similarly, if in that you said, OK, the length of this versus the length of that, length is built-in, but it's not static. You can change length. You can even swap out built-ins and trigger restricted mode. But you can even swap out built-ins and provide your own length function that gives you length plus 1. And because there's all this dynamism, it prevents you from performing certain static optimizations. In the absence of these static optimizations, even though one line of Python code can deterministically map to a set of lines of C code, it's just going to be a lot of lines of C code because those have to figure out all of these different steps of what is this object, what are the built-ins that I'm using, loading everything dynamically rather than being able to statically determine, being able to take a single computation and specify it to the types that are involved. However, this topic that you can take certain lines of Python code and map them to C code is essentially what the pure embedding is. So the pure embedding is, this is the exact same program as before. Everywhere that I see some line of Python code, I can figure out what's the corresponding C code. So here, and you can see this is extremely tedious. So I still have the pi initialized that I had before, but now instead of creating a string that I execute that itself constructs strings, I have to use pi string from string, which creates a Python string from a C string. And then I have to load the built-in module by first creating a string that corresponds to the built-in module, and then using pi import _ import, which imports a module by the name of the module, where the name of the module is a Python string. And then I have to do PyObject getAttr, which gets an attribute from a Python object given a Python string corresponding to the attribute's name. And then I have to create PyTuples, because these arguments, as we saw in the very first example, in the example with keyword unpacking, you have to pass PyObject call a tuple of its arguments and a dictionary of its arguments if it takes keyword arguments. So I actually have to construct a packed tuple of the arguments to call it. So this here is the line that calls the first argument type with the value, the second argument type with the value. And then down here, I multiply them together, and then I do some stuff to print it out. So this is actually, what do I call it? Pure embedding. So I have the same program as I had before, right? But now, instead of just passing it off to the interpreter, I have now encoded each of the steps that the interpreter itself would take, specifying it to certain internal details that I know about the interpreter. And I have the same program. But what I could do here at any one of these steps is you can see that I have all of the result values accessible to me. So at this step, I can do things like I can print them out in different ways. I could do dispatch based on the return value here. I could actually inspect the computation as it goes. So the pure embedding is an embedding that's very useful in cases where you need to have access to the computation as it runs. So for example, you have some large C++ application or some C application, and you want to run custom Python code here or there, but you want to interact with it after the computation ends. You can't just send it off to run. It's not like shelling out. You actually want to directly interact with it. And that's where the pure embedding comes in. Except you can see this is an extremely tedious process, which leads us into Cython. But before we go into Cython, I want to show you extension modules. So I have two modules up here, math module and iterative module. And these are two very interesting modules that are in the standard library that show you what happens when you write code in C for Python. So the itertools module, you can see all your favorite elements of the itertools module are in here. So chains in here, and these are all objects. And there's a lot of boilerplate here for setting them up. If you look at from iterable, chain from iterables in here, and you can see all the doc strings are in here. And it's not too much. And you can see this is a struct that corresponds to all the different pieces of the standard Python object. So there's a get adder, generic adder. There's the deallocator. There's a doc string. Here's the name that you see in Python here. There's a traverse. There's an iteration. There's not too much that's interesting in here. There's methods. So those are the methods that the chain object has, from iterable, for example, which corresponds to a function chain new from iterable, and so forth and so on. The math module is similarly not terribly interesting, but it's a view into how these two work, because we're going to see these very shortly. You can see here are all the math functions that you have in the math module. Here's the C functions that correspond to them. And if you look into this, you look at math floor. Oh, I always need C tags. So let's go into. Oh, it's not. It's hard to find some of this stuff. If you look through, you'll find that these are very thinly wrapped on top of the. What's a good example of something that's not that thinly wrapped? All of these are very thinly wrapped, but you can see that these are just very thinly wrapped on top of the standard C standard lib math functions. So with that aside, put to the side, we're going to look at Cython. So what is Cython? Cython is a tool for transpiling Python into C. And it does something akin to what we did manually in the pure embedding, but it does it automatically with all the boilerplate intact. I'm going to start with this Python module, which implements a function called foo, and we've seen this function twice before already. I'm going to run it with Cython. Here's my makefile. I'm going to run it with Cython. Well, this isn't quite. Yeah, I'm going to run it with Cython right here. And with Cython, I call Cython on the module, and it produces a C file with the module in it. And if I were to look at that C file, this is what it would look like. And it is a nightmare to read through. You can see there's an enormous amount of boilerplate in here. And if you have to scroll down, it's 2,000 lines of code. It is an automated fashion to create this pure embedding, but in no way is it like most automatically generated code, it is extremely verbose. But if we look through this deeply enough, we'll finally find this function that we created. You see there's all this stuff, bisect code objects. There's an enormous amount of boilerplate around this. And if we go through this far enough, we called it, thankfully in this example, we called it foo as opposed to f. We can eventually find, yeah, there we are. Nope, it's actually not even that one. if we search through this enough times, we'll eventually find the actual function code. Here we are. So here we have a C function that corresponds directly to the Python code that we wrote. And if we look very closely at this and we squint hard enough, we'll see that this actually matches to what I wrote by hand very closely. You can see that there's a get attr here. We create a new tuple. We call the object with that. It's obscured by a lot of boilerplate. And then finally in here, we'll see there's a pi number multiply corresponding to the multiplication. Here's the pi object call that created the first object, and the other pi object call up there. There's a pi number multiply right there. So this is essentially the pure embedding that I showed you before, but done by automatically generated code. Well, here's the thing. If we go to the top of this, we'll see that there's a static qualifier. Oh, on this one there's, so let me, okay, so let's do that again. Foo, we'll find it towards the bottom. We'll see there's a static qualifier here. And what the static qualifier in C means, this function can't be seen outside of the compilation unit. So we can't reference it from somewhere else. If we were to remove the static qualifier from here, both from the prototype and the function itself, it's a fairly small change to the file. So you can see I just removed the static qualifiers. And with that, I can now link directly against that function. So I can write this, which is a C program that calls into Cython code directly. And all I did was remove some static qualifiers. Well, one interesting thing here that we can see is that this may be a way for us to write a very, still a fairly tedious, but a very interesting pure embedding. Because what we could potentially do in this case is generate Python code. Well, what this shows is that we can in this, which is no longer, and here's actually the really interesting. This guy does not link against, where's my linking? Here, you can see, oh no, it does link against Python.so. Yeah, so the idea here is if we want to remove this link dependency against Python.so, what we can do is we can use Cython to translate Python code into C code. And if we do that and then take it to its extreme, we could end up with something that can manipulate Python structures without actually having an interpreter. So if you look at this, you can see right up here, this here is just C code, right? And this is just a C program. And the only reason I'm looking against the Python interpreter is because I need to do this PyString from string. But PyStrings are just structs, and I could have created these structs directly. I could just fill in the values directly, because I know how they work. And they don't have to be garbage collected, because nothing in this program outside of what's happening inside the function itself needs to be garbage collected. If I can remove that dependency there, I can then embed Python into a C program without using the garbage collector. And if I take this to its tedious and logical extreme, I can then create what's a zero interpreter embedding. I can take just the pieces of the CPython source code that I need to perform what I want to do, embed them into a C application, and leave out the rest of the interpreter that I don't need. So I could end up having a weird embedding where I have code that may have originally been Python, transliterating into code that is C, that has removed a lot of the dependencies that make Python a full interpreter. This is a very theoretical example that is probably far too tedious to ever do. But it does kind of set up the next and the wackiest embedding. So I showed you extension modules before. And here I have a simple extension module that I wrote. And I call it _python3_. And all it does in here is I use this very high-level embedding thing to do a PyInitialize. And I create a simple function inside this that does pyrunSimpleString. The question that I had here was, could you create an extension module that embeds a Python interpreter so you could run Python from within Python in the same process space without shelling out? And it turns out you can't, because pyrunSimpleString is called pyrunSimpleString in Python 2 and Python 3. On the plane over here, I was playing around with C types and CFFI to see if you could use lazy binding of the symbol names to not have to do any source code rewriting. It turns out that it's still very difficult to do. So what I did was I wrote a source code filter where I used object dump and nm to go through all the publicly exported symbols of Python 3 and rename them with the prefix py3_. And after about an hour or two of trial and error, I managed to create a branch of the Python 3 source code that had every symbol renamed, so there would be no symbol conflicts, so that when you call pyrunSimpleString in something linked, you don't end up conflicting with the ones that are in your Python 2. What I ended up with is a Python 3 that can then be embedded in a Python 2 interpreter. So I'll show you this. And this is pretty wild. And here's the makefile for it. It does get pretty gnarly. But here we have this guy. Now, I'm going to show you two modules. Sorry, get PID. Because I want to make sure that there's, version info. Version info. So there's no tricks up my sleeve. On the outside, oh, it's not a callable. On the outside, I have Python 2.7.5 running in this process ID, right? And I have a simple function and a simple Python module. And this is an unpatched Python interpreter on the outside, 2.7.5. And here's where I'm going to do something cute. Oh, that's weird. Why do I have a syntax error with print? That's strange. Well, this is in the same process. See, the same process ID. So it's running the same process space with access to all the same memory. And on the inside, I have a Python 3.3. So I have two Python interpreters running simultaneously in the same process space who could potentially access the exact same memory. And all it requires is a little bit of source code filtering. There's no shelling out. There's no magic here. We have two simultaneous Python interpreters running, which is kind of weird. This shows you the extent to which you can take the embedding. All I did was I applied the thoughts of how extension modules work and how the very high-level embedding works. And I created a very simple module that just very high-level embeds another Python interpreter. What I could do is I could, instead of using the very high-level embedding, use the pure embedding. And I could pure embed another Python interpreter. In this case, I can't interact very directly with the code here. It just kind of shoots off and runs in that Python interpreter over there. But what I could do is I could use the pure embedding, and I create a shim. And that shim would just take a Python 3 object returned and give you a wrapped Python 2 object just to handle the differences in the two object models. I could make a slight tweak to the garbage collector so that if there were circular references between the two garbage collectors of the two running Python interpreters, you'd be able to run one more sweep to catch those. And then you'd be able to interact with Python 3 code objects from Python 2. And the last step is I'd write an import hook. And I have a mechanism for actually having import hooks apply to themselves, so you don't have to have anyone set them up. And then you could actually have a Python 3 file that applies an import hook to itself to import a Python 3 interpreter. And you could have a file that runs Python 3 in a Python 2 interpreter, which you'd interact with without having to do any modifications to your Python 2 interpreter. That would be really weird. And you'd be able to run Python 3 modules from within Python 2. Now, the problem with that is that's not what we're supposed to be doing. So I showed this to a friend of mine, and he said, you did it the wrong way. You're supposed to be running Python 2 modules from Python 3. But anyway, I thought it was a very interesting example, and it's a logical extension of the things that we've looked at over the last time. So I think with the people shuffling in, we're about done with our tutorial. I guess we have a few minutes for questions, but I thought that was a very interesting example. And I'd love to hear what you guys think. In the back. I'm sorry? So what happens if you go into the dictionary, right? So if you look into the Py dictionary, so one of the questions we looked at before is why. It was a kind of cute question, but hash of -2 is -2, hash of 2 is 2, hash of -1 is 1, and hash of 1 is 1. So there's some pattern that's broken here where hash of -1 always comes out to -2. And we looked at the reason for that. And the question is, well, what happens if we put it into a dictionary? How do we resolve this? Well, if you break into the get item code, you'll see that it first looks up the hash. It first takes the hash and looks into that bucket. It gets the object out and checks the object for equality. If that object doesn't match, then it'll do the slow path search. So it still works in dictionary. There's no reason why you can't do. It'll still work. If you do this, right? It's still, and even if you put another guy in here, it'll still do a check for equality. The case here is merely an implementation detail. There's actually no implications on how it works in the hashing. It does mean that you hit a slow path for this number, but outside of that, there's no implications. Any other questions? you guys missed an embedding of Python 3 into Python 2 running in the same process space and how you can do it by yourself. And it turns out it's not too hard. It's just a very logical extension of basic embeddings. And also, we debugged Python from GDB. If there's no questions, I'll show you one last trick, which I thought was kind of cute. So one of the questions was, in one of the previous examples, we looked at this hash function. And I showed you that if you put a breakpoint on call function, you'll always hit, you'll hit every function. So what you can do is, if you look at a C function, so let's see. So I'll start you from the beginning. So the question is, how would you really debug a, how would you debug it in this case? And what you can do is this. So we have a Python 3. So we want to use this Python 3. Actually, OK. So we know that when we do, this is the last thing I'll show you, Python 3. We know that if we have hash, right, we can get its name, right? So we know that this literal string appears somewhere in the source code. So if we grep the source code for this literal string hash, we'll figure out something very interesting. And we'll see this built-in module here. That's one way to do it. Otherwise, if we do this, if we go in the call function, we'll see that this is actually a C function object, and we can get the function name out. So this, if we put a breakpoint on line, the line numbers are all different because if we go into call function, we'll see at this point right here, we can actually interrogate the currently running function to see what its name is. So if we put a breakpoint here, we want to run this with GDB, run it, put a breakpoint, 4045, continue, hash -1, we can break here. And what we can do is we can actually interrogate this for its name, right? So what we can do in this case is we can put a conditional breakpoint here. I thought this was cute. 4045 if and now this breakpoint will only be hit if you're calling the hash function. So now we can do any other function, we can call any other C function, but it'll only hit if we call hash, if I did that right. And I probably put the breakpoint in the wrong place anyway. But that's, I thought, something relatively cute. So that's one last thing. It's in the extended part of the notes. I guess nobody has any questions, but thank you so much for attending. I thought that was